When the lead on a wire is increased slowly from 4 kg to 8 kg, the elongation increases from 1 millimeters to 1.6 millimeters. If G is equal to 10 in 10 meter per second square, then the work done during the extension of the wire is, here are the options. Now the formula for work done is W is equal to half F2 E2 minus half F1 E1, where F is the force and E is the extension. Now here F2 will be mass into acceleration m2 into a is which is a is acceleration is g, which is 10, and mass second time is 8, which is 8t. Now the extension, now substituting the value here, we'll get half into f2 is 80 and e2 is 1.6 millimeters, which is 0.0016 meters. So on substituting this, we get the answer as 40 into 16 into 10 raised to minus 4, which is equal to 640 into 10 raised to minus 4. Now here f1 is given, f1 on calculating f1 we get 40, since 4 into 10 is 40. Therefore here on calculation will be half into 40 into 0.001. So here we'll get the answer as 20 into 10 raised to minus 3. Since here is the minus 3, we'll convert this to minus 3, which will give us 64 into 10 raised to minus 3 minus 20 into 10 raised to minus 3, which gives the answer as 44 into 10 raised to minus 3. Since the answer is in 4 point, we'll take another, we'll shift one more value, which will get 4.4 into 10 raised to minus 2 joules. Hence the work done is 4.4. The correct answer is option B. The stress versus strain graphs for the wires of two materials A and B are as shown in the figure. If YA and YB denote the Young's moduli of A and B, then we have to find the relationship between YA and YB. Now we know that the Young's modulus Y is equal to stress upon strain, which is equal to the slope, where the slope is equal to tan theta. Therefore, YA upon YB will be equal to tan of the angle. Now here YA has an angle of 60 degrees, therefore tan theta will be 60 degrees, tan 60, and YB has an angle of 30, which is tan 30. Therefore tan 60 is root 3 and tan 30 is 1 by root 3. Therefore root 3 will go up and will be multiplied, which will be equal to 3. Therefore YA will be 3YB. Therefore here the correct answer will be option D. For a given material, the Young's modulus is 2.4 times its modulus of rigidity. What is the value of its Poisson's ratio? Here are the options. Now, Young's modulus is given by y is equal to 2 into the modulus of rigidity into 1 plus the Poisson's ratio. Now, it is given as y is given as 2.4 into n into the modulus of rigidity. Therefore, substituting the value of y, we get 2.4 is equal to 2 into modulus of rigidity 1 plus the Poisson's ratio. Now cancelling the modulus of rigidity on both sides, we get 2.4 is equal to, and substituting 2 inside, we get 2 plus 2 into the Poisson's ratio. So 2 into Poisson's ratio will be equal to 1.4. Therefore will be equal to 0.2. Therefore here the correct answer is option C. Which one of the following is the correct statement from the given graph of extension against load for four wires of the same material and same thickness? Here is the graph. Now here are the options. Either D has the largest length, or C, or B, or A has the largest length. Now we know that Young's modulus Y is given by mgl upon pi r square E. Therefore here the answer is associated with length, therefore we'll take length on the left side. So L is equal to y into pi r square E upon mg. Therefore we can say that L is directly proportional to E upon mg, which is also the slope of the graph. Therefore whichever has the largest slope, now slope is defined by tan theta, so whichever has the largest angle will have the largest length. So here A has the maximum length since its slope is maximum. Therefore the correct answer is option D. A has the largest length. The breaking stress of a cylindrical rod is 10 raised to 6 nano per meter square. If the maximum possible height of the rod is 10 meters, then the density of the material of the rod is, here are the options. Now here G is given as 10 meter per second square. Now we know that stress is equal to force upon A, which is equal to mg upon A, which is equal to V into rho upon G into A, which is equal to A into H into rho into G upon A. A gets cancelled. Therefore, stress is equal to H into rho into G, where rho is the density. Therefore, to find out rho will be equal to S upon Hg. Now, S is given as 10 raised to 6, height is given as 10, and G is given as 10, which will be equal to 10 raised to 4. Now, S is given as Newton per meter square. H is in meters, which is 1 upon m, and G is in meter per second square, which is equal to meter raised to second square. So here the symbol will be second square upon meter raised to 4 into Newton is kg meter per second square. The second square will get cancelled and meter will become kg meter per cube. Therefore, the correct answer is 10 raised to 4 kg meter per cube, which is option C. Strain energy of a wire is 1.8 into 10 raised to minus 3 joules, and strain energy per unit volume of the same wire under the same condition is 6 into 10 raised to minus 3 joules per meter cube. The volume of the wire will be, here are the options. Now we know that volume is equal to strain energy upon strain energy per volume. Therefore, here the strain energy is 1.8 into 10 raised to minus 3 joules, and the strain energy per volume is 6 into 10 raised to minus 3 joules per meter cube. Joules will get cancelled, and this on division will get 0.3. Meter cube will go up to be meter cube. Therefore, the correct answer here will be option B. A long wire hangs vertically with its upper end clamped. A torque of 6 nanometers is applied to its free end and twists it through an angle of 30 degrees. The potential energy of the twisted wire is A 0.57 joules, B 1.57 joules, C 2.5 joules, and D 3.5 joules. Now here the potential energy PE will be given as half into the torque applied into the angle theta. So here the torque applied is into 6 and the angle is 30 degrees, which is pi by 6. Therefore 6 will get cancelled and pi upon 2 will be equal to 3.14 upon 2, which is 1.57 joules, which is option B. So here the correct answer is option B. A wire can be broken by applying a load of 15 kg weight. The force required to break the wire of the same length and material but of twice the diameter of the wire will be, here are the options. Now, a wire of a uniform length of uniform radius can be broken with a force of 15 kg per weight. Therefore, a wire of twice the diameter, which is 2r, twice the radius, will be broken by how much force? Therefore, to calculate force, force will be equal to 15 into 2r square upon pi r square into pi. Pi will get cancelled. 15 into 4 into r square upon r square. R square will get cancelled. 15 into 4 will be 60 kg weight. Therefore, here the correct answer will be option C. When a liquid of volume 4 liter is subjected to an additional pressure of 5 into 10 to 7 Newton per meter square, the change in the volume of the liquid is found to be 4 milliliters. In this case, the bulk modulus of the liquid is, here are the options. Now, the bulk modulus K is given by K is equal to the volume into the change in pressure upon the change in volume. Now, we know that V is given as 4 liters, therefore 4 into 5 into 10 raised to 7. Now, the change in the volume of the liquid is given as 4 milliliters, which on converted into liters will get 4 into 10 raised to minus 3. Therefore, 4 will get cancelled and minus 3 will become plus 3 when it goes up. Therefore, 5 into 10 raised to 10 Newton per meter square. Therefore, here the correct answer is option B. In brass, the velocity of longitudinal waves is 2 times the velocity of transverse waves. If y is equal to 1 into 10 is to 11 nanonewtons per meter square, then the stress in the wire is, here are the options. Now the velocity of the longitudinal waves VL is given by root of E upon rho, which is equal to root of Y upon rho. Now V of the transverse waves is equal to root of T upon M, which is equal to root of mg upon pi r square upon rho. Now on taking the ratio, we get VL upon VTR is equal to Y upon rho into pi r square rho upon mg. Rho will get cancelled, which will be equal to root of y upon taking pi r square upon on below we get mg upon pi r square, which is the stress, which will be equal to y upon stress. Therefore, to remove the root sign, we need to square both sides. Therefore, VL upon VTR the whole square will be equal to y is given as 1 into 10 raised to 11 upon stress. Now, since VL, therefore, we'll get 10 raised to 4 is equal to 10 raised to 11 upon stress. Therefore, stress will be equal to 10 raised to 7 Newton per meter square. Therefore, the correct answer is option A. A metallic rod breaks when strain produced in the rod is 0.2%, the Young's modulus of the material. The rod is 7 into 10 raised to 9 newtons per meter square. What should be its area of cross section to support a load of 10 raised to 4 newtons? Here are the options. Now, breaking breaks the rod breaks when strain is produced in the rod is 0.2% the Young's modulus. Therefore, the breaking stress will be equal to y into the breaking strain, which is 0.2% of the Young's modulus. Young's modulus is given as 7 into 10 is to 9 into 2 upon 1000, which will be equal to 14 into 10 raised to 6 Newton per meter square. But breaking stress is given as F upon A. Therefore, A will be equal to F upon the breaking stress. We have to find the area of cross section. Now we know that F is 10 raised to 4 and breaking stress is 14 into 10 raised to 6, which will be equal to 7.14 into 10 raised to minus 4 meters square. Therefore, the correct answer here is option B. Two wires A and B are of the same length, their diameters are in the ratio of 1:2 and Young's moduli are in the ratio of 2:1. If they are pulled by the same force, then the elongation will be in the ratio. Here are the options. Now the elongation is given by E is equal to mg L upon pi r square into y. Now except r and y, all the other values of both the wires are the same. Therefore, E is inversely proportional to r square into y. Therefore, E1 upon E2 will be R2 square Y2 upon R1 square Y1. Now we know that the ratios of the diameters and the moduli. So substituting the value, we get 2 upon 1 the whole square into half, which is 4 upon 2, which is 2 is to 1. Therefore, the correct answer here is option B. If the stress strain relation for the volume change is of the form delta V upon V0 is equal to K into P, where P is applied uniform pressure, then K stands for, here are the options. Now the bulk modulus B is given as V0 into the change in pressure upon change in volume, which is equal to, if we take V0 below, we get dP upon dV upon V0. Therefore, we get dV upon d0 dv upon v0 equal to dp upon b, but here it is given as delta v, which is dv upon v0 is equal to k into p, where k is a constant. Therefore, substituting the value, kp will be equal to dp upon b. Now we can cancel b since the change in pressure is the same. Therefore, K will be equal to 1 upon b, which is equal to the compressibility, which is 1, b is the bulk modulus, which will be equal to compressibility. Therefore, the correct answer here is option D. A cube at temperature 0 degrees is compressed equally from all sides by an external pressure P. By what amount should its temperature be raised to bring it back to the size it had before the external pressure was applied? The bulk modulus of the material of the cube is K and the coefficient of linear expansion of its material is alpha. Here are the options. Now, we know that the bulk modulus K is equal to V into dP upon dV. Therefore, dV will be equal to V dP upon K, where dV is the decrease in volume. But in this case, dP is equal to P. Therefore, dV will be equal to Vp upon K. Now, to increase the volume by dV, we have to increase the temperature by dt. Therefore, by definition, gamma will be equal to dV upon V into dt. Therefore, dV is equal to V into gamma into dt. But gamma is equal to 3 alpha. Therefore, dV will be equal to 3 alpha V dt. Now from now let this equation be 1 and this equation be 2. Therefore, we have two values of dV. Therefore, from 1 and 2, we get Vp upon K will be equal to 3 alpha V dt. Therefore, we need to find the value of the temperature. Therefore, dt will be equal to Vp upon 3 into alpha V K. V and V will get cancelled. Therefore, dP will be equal to P upon 3 alpha K. Therefore, the correct answer here is option D. A steel ring of radius small r and cross-sectional area A is fitted onto a wooden disc of radius capital R, where capital R is more than small r. The Young's modulus of the steel is Y. What is the force with which the steel ring is expanded? Here are the options. Now, in this case, the area of the steel ring A is equal to pi r square. Now, the original length L will be equal to 2 pi r, which is equal to the circumference of the ring. Now, the ring is fitted in circumference. Now, the ring is fitted on the disc. Therefore, the change in length delta L will be equal to the increase in length of the wire of the ring, which is equal to the circumference of the disc minus the circumference of the ring, which is equal to 2 pi r minus 2 pi small r, which is equal to 2 pi into capital R minus small r. Therefore, here the Young's modulus Y will be equal to F into L upon A into delta L, which is equal to F into 2 pi r, which is the length, upon A into 2 pi into R minus r, which is equal to, since 2 pi gets cancelled, Fr upon A into R minus r. Therefore, the force applied will be F is equal to Y into A into R minus R upon R. Therefore, the correct answer here is option C. When a wire is stretched, the increase in its length is 0.02%. What is the percentage decrease in its diameter if its Poisson's ratio is 0.3? Here are the options. Now, the Poisson's ratio is given by minus delta D upon delta L upon L. Therefore, minus delta D upon D will be equal to the Poisson's ratio into delta L upon L. And the percentage decrease in diameter is given by minus delta D upon D into 100. Therefore, substituting the value of minus delta D upon D from here, we get Poisson's ratio into delta L upon L into 100. Now, Poisson's ratio is given by 0.3 into 0.02% is the increase in its length. Therefore, 0.02 upon 100 into 100. This will be equal to 0.006. Therefore, here the correct answer is option B. When a 4 kg mass is hung vertically from a light spring that obeys Hooke's law, the spring stretches by 2 cm. The work that should be done by an external agent in stretching this spring by 5 cm will be A 1.5 joules, B 1.75 joules, C 2 joules, and D 2.5 joules. Now here we know the force and the length with which it stretches. Therefore, K is equal to F upon X equal to 4 into 10 upon 0.2, which is equal to 2000 kg per meter. Now the work done will be given that work done is equal to half into K into X square, which is equal to half into 2000 into 0.4 the whole square, which is given by 2.5 joules. On calculation, we get the answer is 2.5 joules. Therefore, here the correct answer is option D. A long wire is stretched by 0.25 centimeters. The energy stored per unit volume is 0.2 joules per meter cube. When it is stretched by 1 centimeter, the increase in the potential energy per unit volume stored in the wire is given by, here are the options. Now we know that potential energy per unit volume is equal to PE into half into Y into the strain square. Therefore, PE, we can say PE is directly proportional to the strain square. Therefore, when the long wire, when 0.25 into 10 raised to minus 2 meters of wire stretch, the potential energy per unit volume stored is 0.2. Now, when it is stretched by 1 centimeter, how much is the potential energy? Therefore, 0.2 upon x will be equal to 0.25 into 10 raised to minus 2 upon 1 into 10 raised to minus 2 the whole square. Therefore, x will be equal to 16 into 0.2, which is equal to 3.2. Therefore, the increase in the potential energy per volume will be 3.2 minus 0.2, which is equal to 3 joules per meter cube. Therefore, the correct answer here is option B. One end of a uniform wire of length L and weight W is attached rigidly to a point in the roof, and a weight W is suspended from its lower end. If S is the area of the cross section of the wire, then the stress in the wire at the height of 3 into upon 4 into L from its lower end is, here are the options. Now suppose this is the ceiling and this is the wire where the weight W is attached right over here, where the downward force acting on W will be W1. Now we need to find here is the area which is at 3 upon 4 from the lower end. Here is W. Therefore, the downward force acting on A will be equal to the weight of 3 upon 4 the length of the wire plus the weight attached which is W1, which will be equal to 3 upon 4 W plus W1. Therefore, the stress will be equal to F upon A, which is equal to W1 plus 3 upon 4 W upon S. Therefore, here the correct answer will be option C. Indian rubber and cord L meter long and area of cross section A meter square is suspended vertically. Density of rubber is Y Newton per meter square. If the cord extends by L meter under its own weight, then extension L is, here are the options. Now for considering the extension, we consider half the length, which is L by 2, because the weight acts through the center of the gravity. Therefore, the strain will be equal to L upon L by 2, which is equal to 2L upon L. And the weight of the cord will be equal to mg, which is equal to V into rho into G, which is equal to A into L into rho G. Therefore, the stress will be equal to F upon A, where F is this, where into rho into G upon A. A will get cancelled and L into rho upon J. Therefore, the Young's modulus Y will be equal to stress upon strain. Stress will be equal to L into rho into G upon strain, which is 2L upon L. Therefore, which is equal to L square rho G upon 2L. Therefore, we need to find the value of L. L will be equal to L square rho G upon 2Y. Therefore, here the correct answer will be option B. Gas is heated at constant pressure. Its isothermal compressibility A decreases linearly with temperature. B increases linearly with temperature. C decreases linearly with temperature. Or D remains constant. Now, here isothermal electricity, i.e., of gas, is numerically equal to its pressure. Therefore, isothermal compressibility IC will be equal to 1 upon P, but P is kept as constant. Therefore, isothermal compressibility will also remain constant. Therefore, here the correct answer is option D, remains constant. Modulus of rubber is 9 into 10 is to 8 Newton per meter square. To what depth a rubber ball be taken in a lake so that its volume is decreased by 0.1%? Here are the options. Now the bulk modulus is given as K is equal to V into dP upon dV, which is equal to dP upon dV upon dV slash V. Now where dP is equal to H into rho into G, which is equal to H into 10 raised to 3 into 9.8. We need to find the value of H. Now the change in the volume will be given by 0.21%, which is equal to, it is actually 0.2%, which is upon 100, which is equal to 2 into 10 raised to minus 3. Therefore, because K is equal to dP upon delta V slash V, therefore 9 K is given as 9 into 10 raised to 8, which is equal to H into 10 raised to 3 into 9.8 upon 2 into 10 raised to minus 3. Therefore, H will be given by 1.83 into 10 raised to 2, which is 183 meters. Therefore, here the correct answer is option D. Versus elongation graph for four wires of the same length and material is represented by the four lines OA, OB, OC, and OD as shown in the figure. Which line represents the thinnest wire? Now, we know that the Young's modulus Y is equal to mgl upon pi r square into E. Therefore, E will be equal to mgl upon pi r square E. Therefore, we draw a line parallel to the E axis like this. For this line, load W is constant and the wire A has the maximum extension. We draw a line parallel. Now, for the wires of the same material, Y is constant. Hence, for the same M and L, E is inversely proportional to pi r square. Therefore, when the extension is maximum, the radius will be minimum. Now, from this graph, we see that A has the maximum extension. Therefore, it will have the minimum radius. Therefore, it will be the thinnest since it has the minimum radius. Therefore, the line OA will be the thinnest wire. Therefore, the correct answer here is option B, OA. For a metal, the Young's modulus is given by 7.2 into 10 to 10. The bulk modulus K is equal to 12 into 10 to 10. What is the Poisson's ratio for the metal? Now, the Young's modulus, the bulk modulus, and the Poisson ratio is associated with this equation. Y is equal to 3K into 1 minus 2 into Poisson's ratio. Therefore, Y upon 3K will be equal to 1 minus 2 Poisson's ratio. Therefore, Poisson's ratio will be equal to half into 1 minus Y upon 3K, which is equal to half into 1 minus 7.2 into 10 raised to 10 upon 3.12 into 10 raised to 10. Therefore, this will be given as half into 1 minus 0.2, which is equal to half into 0.8, which is equal to 0.4. Therefore, the correct answer here will be option D. Rubber cord catapult of unstretched length 10 centimeter and cross-sectional area 1 millimeter square is stretched to 12 centimeter and then used to project a stone of 5 gram. What velocity the stone is projected if the Young's modulus of rubber is 5 into 10 is to 8 newtons per meters. Now the strain will be given as the change in length upon the original length, which is 12 minus 10 upon 10, which is equal to 1 by 5. Now the volume of the cord V is given by A into L, which is equal to 1 into 10 raised to 6 into 0.1, which is equal to 10 raised to minus 7 meter cube. Mass of the stone is given in grams, which is 5 into 10 raised to minus 3 kilograms. Now the kinetic energy of the stone, Ke of the stone, will be equal to the elastic potential energy of the rubber cord. Therefore, half mv square will be equal to half into y into the strain square into the volume of the cord. Therefore, V is equal to root of y into strain square into V upon m. Therefore, on substituting the values, we get 5 into 10 raised to 8 into 1 upon 5 the whole square into 10 raised to minus 7 upon 5 into 10 raised to minus 3, which is equal to half 1 by 5 into 100, which is 20 meter per second. Therefore, the velocity will be 20 meter per second. Therefore, the correct answer is option D. Longitudinal extension of an elastic material is very small. In order to have an appreciable change in length, the material must be in the form of short thin wire, thin block of any cross section, long thin wire, and D, thick block of any cross section. Now the Young's modulus Y is given as mgl upon pi r square into the change in length. Therefore, the change in length is equal to mgl upon pi r square y. Now y, pi and mg are all the same for the wire. Therefore, we can say delta L is directly proportional to L and inversely proportional to the r square. Now thus for an appreciable change in the length of the same wire for the same load, the L should be more and the r should be less. Therefore, in this way, if the load is more and the radius is less, the change will be appreciable, which is more. Therefore, a long thin wire is required. Therefore, the correct answer here is option C. Spring of an unstretched length L and spring constant K is stretched by a small length X. It is further stretched by another small length Y. The work done in the second stretching is, here are the options. Now the potential energy stored in the spring while it is stretched by length X is given as half into K X square. We can say that this is U2, U1. Now, when it is stretched by a further distance y, the potential energy U2 will be half into k into x plus y square, the whole square. Now the work done will be given as U2 minus U1. Therefore, half into k is same x plus y the whole square minus x square, which is equal to half into k x square plus 2xy plus y square minus x square. X square will get cancelled. So we will get w as half k y will be taken common 2x plus y. Therefore here the correct answer will be option C, half into k into y, 2x plus y. Gas, the pressure is changed from 1.01 into 10 raised to 5 pascals to 1.165 into 10 raised to 5 pascal, and change in the volume is 10%, keeping the temperature constant. The bulk modulus of the gas is, here are the options. Now for the gas, the change in pressure dP is given by 1.165 minus 1.010 into 10 raised to 5, which is 0.155 into 10 raised to 5 Newton per meter square, which is equal to 1.55 into 10 raised to 4 Newton per meter square. And the change in volume dV upon V is 10%, which is 10 upon 100. It is equal to 1 by 10. Therefore, the bulk modulus K will be given as dP upon dV upon V, which is equal to 1.55 into 10 raised to 4 upon 1 upon 10, which will be equal to 1.55 into 10 raised to 5 Newton per meter square, which is pascals. Therefore, the correct answer here is 1.55 into 10 raised to 5, which is option D. Constant hydraulic pressure on an object, the fractional charge in the object's volume delta V upon V and its compressibility 1 by K are related as. Here are the options. Now the bulk modulus K is given by K is equal to V dP upon dV numerically. Therefore, 1 by K will be equal to dV upon V into dP. Therefore, dV upon V will be equal to dP upon K. Now, if dP is kept constant, therefore the dV upon V will be directly proportional to 1 upon K, where 1 upon K is the compressibility. Therefore, here the correct answer is option C. The adjacent graph shows the extension delta L of a wire of length 1 meters suspended from the top of the roof at one end and with a load W connected to the other end. The cross-sectional area of the wire is 10 raised to minus 6 meters square. What is the value of the Young's modulus of the material of the wire? Now here is the graph given of delta L against the weight attached. Therefore, the Young's modulus y is given by y is equal to mgl upon a into delta L, which is equal to wl a delta L, which is equal to w upon delta L upon a. Now the graph of delta L upon W is a straight line. Therefore, it is a constant. Therefore, delta L upon W is a constant. Therefore, W upon delta L will be equal to 20 upon 10 raised to minus 4. Therefore, the Young's modulus will be given by 20 upon 10 raised to minus 4 into 1 upon 10 raised to minus 6, which is 20 into 10 raised to 10, which is 2 into 10 raised to 11 Newton per meter square. Therefore, here the correct answer is option A.